An hyperbola, when sketched, looks like two graphs in one. The formula looks like this. So you've got a over x plus q. Just like the parabola, the q value indicates a shift up or down. And obviously, if it is a positive number, you're going to shift up. And if it is a negative number, you're going to shift down. The a value is the vertical stretch, and it's going to dictate how close the arms of the hyperbola are to the axes. So this is the vertical stretch. The other thing that the a value tells you is the position of the two pieces of the hyperbola graph. So, if the a value is positive, so if the a value is positive, you're going to have a hyperbola that looks like that. The two parts of the graph will be in that quadrant and that one, where both x and y are positive and both x and y are negative. If you have a negative a value, and those are the axes, then the hyperbola will be there. Notwithstanding, of course, it could shift up and down, but you get the idea that it's top right, bottom left, or if negative, top left and bottom right. To show you how to draw hyperbolas, I'm going to show you two examples. One where the a value is 6, which is a positive number, and the q value is 2, which is also a positive. So this one's going to dictate the position here and the stretch, and the positive 2, which is the q value, indicates that the graph has shifted up from its original position. As usual, we need to know where the intercepts are to be able to draw the graph. So for this one, we're going to find the x-intercept, which means we let y equal 0. So that means that this graph equals 0. So I'm going to say 0 equals 6 over x plus 2. Moving the 2 across, I've got negative 2 is 6 over x. And then if I cross multiply, I have negative 2x equals 6. This means that x equals negative 3. Because it's an intercept, I need to write down the point, and I must remember that intercept means that one of the coordinates is 0. Because I'm finding the x-intercept and I let y equal 0, it means that the y is the 0 and the x is the one I've just worked out. It's useful to write down the point because then I remember to plot that point and I don't go and connect it to something else. Okay, so what happens with the y-intercept? This is an interesting question. If I try to work it out and I let x equal 0, I have a big problem because that means that I have 6, so I'm going to say y equals 6 over 0 plus 2. This is undefined. And that's important because that will help us understand something else that's very special about a hyperbola. A hyperbola is a graph with two parts to it. The one we're going to draw is going to have two parts of the graph that are in the top right and the bottom left. Now what's happening over here is that the graph is approaching the axes. And in this example that I'm showing, the axes act like asymptotes. An asymptote is something that we will find in other graphs again, but this is the first time we've come across it, so we'll define it here. An asymptote this is a line that the graph approaches, so moves towards, but never crosses or touches. When we get something that's undefined, what we know is that there is no place where x equals 0. So clearly the line x equals 0, that whole place where x equals 0, you don't have part of the graph. The line x equals 0, if we take this as a line, it's going to be the asymptote. The line x equals 0 is the y-axis. That is the line x equals 0, and obviously the x-axis is the line y equals 0. That is an asymptote. Okay, so here this means that x equals 0 is the asymptote, and that is like that for all of the hyperbolas we do this year. We're going to be shifting left and right in grade 11 where that asymptote will change. So x equals 0 is the asymptote that is vertical. We're also going to have a horizontal asymptote, and that's going to be quite easy to find. The next step is to write down the horizontal asymptote. And you just read that off the Q value. So we're going to add that to our labeling of the formula. This, the Q value, is also the value of the horizontal asymptote. So when you are getting the horizontal asymptote, you're basically reading off the formula for the graph. The horizontal asymptote is the line y equals q. So it's going to be, what is q in this case? Q is 2. So it's going to be the line y equals 2. So those are our two asymptotes. And that's the second thing to do when finding things to draw on this graph. So it's different to the parabola, different to the straight line. Here they are asymptotes and they need to be plotted. We're going to plot these lines. Well, this one's already going to be on the Cartesian plane, so no need to do it. This one we're going to plot using a dotted line all the way across the Cartesian plane. Having the information we've got so far is not enough. To be able to plot these graphs, we need a little bit more. So we're going to use what I'm calling a strategic table method. So previously with table method, we use the calculator and we sub in -3, -2, -1, 0, 1, 2, 3. Now first of all, plotting in x is 0, we know what we're going to get. We're going to get a math error. So that's not going to help. Now what will help, and what will be able to give us points we can plot, will be if we find things where this works out very nicely. 6 over x is something. So we're going to use factors of 6, because that will help us find numbers that are whole numbers, which are just easier to plot than other numbers. So I want some negative and some positive. I'm not including 0 because I know where that gets me, and at this point it's really unhelpful, and I've already done it, so I don't need that. So I'm going to look at the factors of 6. So I'm going to go -6 and let's say -3. I could use -2, -1. I'm just trying to get a bit of a spread. I'm not using 0, and then I'm just going to do the other ones that are positive. Okay, when I sub that in to the formula, I'm going to get out these answers. And those are the points that I'm going to plot in addition to my asymptote and the intercept that I could find. Okay, so the best idea is to start with the asymptote. My asymptote is the line y equals 2. This is the y-axis. The line y equals 2 goes over there. It's horizontal asymptote. When I plot the asymptote, I am going to label it, and I'm going to plot it using a dotted line. And that indicates it's a line that this graph may never touch. So I will label it, and then I'm going to plot in some other points. Now, I know because the A value is positive that I'm going to have a graph where the 2 bits lie top right and bottom left. So I'm expecting that, and if that's not what I get, I've probably made a mistake in the table. Okay, so plotting x is -6 and y is 1. So these I've done as centimeters, and -6 will obviously be here. 1, 2, 3, 4, 5, 6, that's -6, and 1. -6 and 1 is over there. I'm going to label the points at the end. Then another point that I'll plot will be -3 and 0, which I actually worked out twice because it was the x-intercept and it was also on my table. So -3 and 0, -3 on the x and 0 on the y is there. Then -1 and -4 is going to be down here, so -1 and -4. And there I've got these 3 points. Now, because it's a hyperbola, we know that we're going to join those and we're going to get another one up here. So it's approaching that asymptote, it never gets there, and it's approaching the y-axis and it never gets there either. This half, I just show my intercept as -3. I'm going to label my points, and then I've done the first half, which is all the negative ones. For the other half of the graph, I'm going to look at my positive x values. So on this side it's positive x values, on that side it's negative x values. Okay, the point 1 and 8. With the axes I've drawn, I can't actually plot that, so I'm hoping the others will be enough, and they normally are. Normally it's intercepts and one other point in the asymptote. So the point 3 and 4 I can do. It's 3 there and up to there. And then the point 6 and 3. So that'll also be above the asymptote. So 6 here and then 3. And that graph will be like that. These are symmetrical, the 2 bits, but you can see I haven't included, it would have gone up there. And that's a perfectly acceptable way of drawing it. So that's the point 3 and 4. And this is the point 6 and 3. I've got my asymptote in, and I've labeled everything that I need to label. With this graph, it's a different formula, and you'll see the A value is negative, and so is the Q value. So already I know I'm dealing with a shape that's not going to be like the previous one there and there. It's going to be here and there, and it's going to have shifted down. So the asymptote's not going to be the x-axis, it's going to be -1. So that's going to help me understand what I'm looking for. Right, so I'm going to try to find intercept where possible. So let's go for the x-intercept. This is where y equals 0. So I'm going to have 0 equals that. So 0 equals -3 over x minus 1. Right, the negative may be there in the middle or the bottom. You're going to make sure you always move it to the top. Just like for calculating the gradient of a straight line, if we keep a convention and we always do it the same way, then we'll confuse ourselves less. So stick to moving it to the top and keeping the number negative instead of the x. It actually doesn't make a difference, it's just easier to work with if that's at the top. So moving the 1 across, it's going to be a +1, and that's going to be -3 over x. Cross multiplying again, that's over 1, so I end up with x equals -3. So that is the point where x is -3 and y is 0. That is a point that can then be plotted. Okay, now there isn't going to be a y-intercept again for the same reason. because this graph is not going to shift left and right, which means it's going to have an asymptote over there on the line that is the y-axis. So there is no y-intercept. Okay. Right, then we're going to use our strategic table method again. Remember here, the strategy is to use factors of the a value. The a value in this expression is -3. So, okay, -3 doesn't have very many factors. It's got 1 and 3. It's a prime number. So I'm going to have to manipulate this a little bit. So I do have to deal with fractions, but I'm going to be in control of that process. Okay, so if I say -3, then when I plug this into the formula with a calculator, I'm going to get out 0, so that's fine. And then I can also do -1. So I'm going to do -1. I'm going to get out 2 as my answer. And then I'm going to try a few in between and see if there's a way I can help the process. Because -3 and 0 again is the intercept, so it doesn't really help me. I've already got it. So let me try -2. When I sub that in, I get a point I can plot. And that's important. You can estimate a half, so that's perfectly fine. Okay, we're not going to do 0 because we know where that gets us. Let's try the opposite ones and see where those go. So this gives me -4. This gives me -5/2, which is -2.5. Now, why am I writing it as a mixed number? Because that's something I can plot. 5/2 is not a number that I can estimate on a graph, but if I know that it's -2.5, I'm fine. So I'm going to see which of those are possible to plot. Here I've chosen axes that are different to the previous one because I've got to accommodate the points that I want to plot. I need to also have my asymptote, so I'm just going to write that down. So my asymptote, I read straight off the graph, it is that. It is the line y equals -1, and that's where I start the plotting process. So when you've labeled the asymptote and a few points, you've effectively labeled the scale of the graph, so you don't have to duplicate there. So if I say that that's y equals -1, it's perfectly obvious that that is -1, -2, -3. Okay, so that is my horizontal asymptote, and the vertical one is the y-axis, the line x equals 0. Right, plotting a few other points, I have -3 and 0, so that's going to be there. And then I have -2 on the x and a half on the y. So that's why I made the scale quite big, so that I can estimate a half. So a half's going to be halfway up there, and it's -2 and a half, so it's going to be that. And then -1 and 2 will be up there. Right, so the shape is doing what it's supposed to do. There's my asymptote. When I connect the dots, it's a curve again with arrows on, and I do need to label my points. So that is -3, and I can just put the 1 because it's clear that it's on the axis. This is -2 and a half, and this one is -1 and 2 on the y. Okay, the other half of the graph will come from these ones. So, and it's going to be symmetrical here. It's going to be in this one because I've moved the whole thing down, so the other half will be over there. So I've got the point 1 and -4. So 1 on the x and -4 on the y. And actually my axes have not gone that far, so I can't plot that, and that's okay. I'll plot the others. What about 2 and -2.5? So 2 on the x and -2.5. Well, that's -2, so, and that's -3, so about halfway there. Should be about right. And if I don't plot it perfectly, the fact that I've labeled it is what I'm going to get the marks for, so that's okay. And then the points 3 and -2, so 3 there and -2 here. Again, I'm just going to sketch it so that it looks more or less symmetrical to the other one. And I'm going to label my points so that if all else fails, it's quite obvious that I have known what I'm supposed to be plotting. And there you go. That is the second hyperbola drawn as a graph. Graph interpretation is going to be all the things that does not involve exactly drawing a graph. So you may have to draw it and then interpret it, or you may have been given a diagram and then you have to interpret from there. Okay, so the first one we're going to look at is transformation. So when we talk about shifts up and down or reflections in the axes, those are ways that the graphs have been transformed to look like other ones. So the first ones that we're going to look at now are when we talk about two graphs and we say, well, the one is the reflection of the other. So reflections we're going to look at. Okay, so if we say, for example, let's look at these two here. Let's say we've got y equals 3 over x minus 1, and then we've got another one, and we say that one is y equals negative 3 over x. So you see what's happened, the 3's become negative, and let's say negative 2. Now what's happened to get from that one to that one? Without even drawing the graphs and without even having a sketch, we can figure out what's happened. Okay, so this means because the a value has gone negative, it means it's been reflected in the x-axis. So what once was this graph over here would have been there, and it would have had an asymptote there of negative 1 and that part there. What's happened with this one is now it's gone the other way around. So this graph is going to have a negative 2, so that's going to be further down, so the whole thing is going to shift down because of the q value changing. But this one tells us that it is now going to be on the different sides. It's going to be top left and bottom right. So that will look more or less like this, with an intercept over there. So what has happened? The graph has been reflected in the x-axis. So here, this one has been reflected in the x-axis, and it's also been shifted down by how much? Well, this was negative 1, and then it went down 1 more to get negative 2. So it's been shifted down by 1. Yes, that's negative 2, but didn't start on 0. It started on negative 1, so it only got shifted down by 1. Remember that shifting is another way of talking about the word translation. Or you can say that the graph has been translated down. So be aware that those two terms can be used. Another form of basic graph interpretation is when you are asked which values of x the graph increases or decreases. So this is the ruler test. You'll remember with parabola, just a little reminder, with parabola, if you had one like that, it would decrease to that point and then increase. Or if it was a sad parabola, it would increase to that point and then decrease. With a hyperbola, it's either going to always increase or always decrease except for the asymptote. So I'm going to use the ruler test and go back to this one and show you what I mean. So this graph, if I move the ruler across and I trace the line, I'm going up, and then it disappears. And then from here, I'm also still going up, and it disappears here. So this is an asymptote that doesn't work there, but I still have an increasing function. So this graph increases the whole time except for the asymptote. This one that we drew first, if I do the ruler test here, it's going down and then disappears and then it goes down again. Also going down the whole time except for the asymptote. So for f of x, the first one, and g of x, the second one, I can write it like this. I can say f of x increases for no values of x and decreases all the time. So if they ask both, I would say for no values of x, it decreases all the time for all values of x except at the asymptote. Okay, you can write that as a sentence. You could say it decreases for all values of x except 0, or I could write it in my set builder or interval notation. So I could say it's for x is an element of anything from negative infinity to 0 not including, because that's the asymptote. It does not do anything at the asymptote. It doesn't even go through the asymptote. So it's for that, and then from 0 upwards to positive infinity, also excluding. Or I could do set builder notation, and I could say it's for negative infinity being less than x, so x is in between negative infinity and 0, and that way it's decreasing there, and then also between 0, so x is between 0 and positive infinity. And what will happen with the g of x function is that it will be exactly the opposite. It will decrease for no values of x, and it will increase for all values of x except those particular parameters. Finding the equation of a hyperbola is all about what you can see on the graph you're given or the information you're given and subbing it in. Okay, so let's say that they give you're given the horizontal asymptote. By that I mean either you can see it on the picture and they show the little dotted line and that's the horizontal asymptote, and they tell you what it is. So they say this is the line y equals -3 or 4 or something. Or they tell you what it is. So be careful, don't get sidelined by the way in which they give it to you. So let's say they give you the horizontal asymptote and then they give you a point. Okay, so the horizontal asymptote is a q value. You plug it straight into your general formula, and then this one, a point is going to have the value x and y. So you plug in the x, you plug in the y, and what's left over, let's go back to the formula, is actually a over x plus q. So you've subbed in the q, you've subbed in y and x, you're solving for a. So you're going to solve for a and get out an answer. You can see why equations are so important, because they get used throughout other forms of mathematics. So you're going to solve for a, but then the most important thing is you're going to put back into standard form, which is that. So you have a y in the formula, you have an x in the formula, but your a value and q value are numbers. You could be given something else, and this leads on to the next form of graph interpretation. I'm going to go back to the previous two graphs and draw in for you the axes of symmetry. An axis of symmetry is also going to be a dotted line, and it's going to show you where the graph could be folded in half on top of itself and be exactly identical. To find the axes of symmetry, you're going to look at where the two asymptotes join. So we know that the one is the one we got, which is y equals 2 for this graph, and the other one is the y-axis, or the line x equals 0. Look at where they cross. That is where your two axes of symmetry are also going to cross. So you end up with like a little asterisk, because these graphs are symmetrical, and it's going to be a line of a 45-degree angle from the x-axis. So that these graphs, if they folded on top of each other, would be directly symmetrical. It's going to be through there, and then it's also going to be this line through there. So there are two axes of symmetry, which is quite special about a hyperbola graph. So that's the axis of symmetry. So that one would work like that, and if I took these two arms here from there, that would fold onto that one. Similarly, this one, we are going to look at where the two asymptotes join, and that is there. And from there, your two lines of symmetry are going to be at a 45-degree angle of those two lines. So we're going to be symmetrical from there to there. So this half and that half are symmetrical, and then it's going to be this one. There is something to memorize about these two straight lines. The one that goes in this direction, so the one that slopes to the right, has a gradient of 1, and the one that slopes to the left has a gradient of -1. Remember that from straight line graphs. So here I've redrawn a basic hyperbola that has the asymptotes on the two axes. so no Q value, Q0, and I put in the 2 lines of symmetry. So this one has a gradient of 1. They're always like this. You just have to remember it off by heart because it slopes to the right, positive gradient. And this one has a gradient of -1. You've got to know that off by heart, and then when you have to find the equation and you are given the lines of symmetry, which you treat as straight lines, you'll be able to work with the information to find the equation. Looking at it differently, the asymptote of your graph will join the 2 lines of symmetry or axes of symmetry at the point where this asymptote cuts the y-intercept. So basically your Q value equals the y-intercept of both axes of symmetry. So you have the y-intercept of that line, and you have the a value of that line because we know that it's always +1. So for this one, a equals 1, and for this one, a equals -1. You've got the gradient, the a value, and you've got the y-intercept. So that means you've actually got the formula for the straight line. As long as you've got the asymptote here, because that is the y value. So you could be asked to calculate the formulas for the axes of symmetry. Reminder, straight line formula is ax plus q. Now your q and your q are the same. It is the y-intercept. So you already have that from your asymptote. And you have the a value because it is either 1 or -1, which you've learned off by heart. So when you've got the formula for the hyperbola, all you're going to do is sub in that from the asymptote and then either 1 or -1, and then you've got your straight line so far. So what this question could look like is they could say give you the axis of symmetry, or more than 1, or they could just give you 1, and then one other point. So they could give you another point x and y. Now if they give you the axis of symmetry, this means that they give you the formula for a straight line, and they want the formula for the hyperbola. So what you want there, if you've got the axis of symmetry, which is a straight line, you're going to use the q value, which is the y-intercept, because they've now given that to you. Okay, what is the q value? For the hyperbola, it's also the asymptote, which is the q value. So the q value is the q value. The q value in the axis of symmetry is the same as the q value in the hyperbola. So you've got that q value, and then they give you one other point. You sub in for x and y, you get a out, and you rewrite in standard form as usual. The other question you can be asked is for domain and range. Remember, domain is the x, how far left and right, and the range is your y values, how far up and down. Okay, so just redrawn or sketch this one so you can see the idea. It links quite closely to finding for which values the graph increases and decreases, because you're doing the same kind of answer even though you're answering a different question. So how far up and down does this graph go? Oh, sorry, let's start with domain. How far left and right does it go? It seems to go infinitely towards the left, and then, okay, asymptote doesn't work. Then it goes infinitely towards the right. So basically it's x is anything except 0, and you can write it like that as well. You can say x is an element of real numbers, x does not equal 0. You could write it like that, or in set builder or in interval notation. The domain is actually the same, excepting it's not for 0. This one, the asymptote was on y equals 2. So it obviously goes, how far down can it go? Well, as far as you like, down to negative infinity, except it can't be 2. And then from 2 up it can go to positive infinity. So we can write that y is anything, excepting y may not be 2.